Welcome to everyone. I will discussing on group theory. And previous class we have discussed all the symmetry operations like identity symmetries, axis of symmetries, plane of symmetries, improper axis of symmetries, and center of symmetries. So today class I will try to discuss, I will try to understand the point group. So if we define the point groups, then it can be defined as that a group of elements. Their elements means symmetry operations. Like a group of elements means a group of symmetry operations. Like we can say CN axis, sigma, and proper axis. All these operations that are interrelated that are interrelated according to certain rules. So if a group of symmetry operations, if they are interrelated to certain rules, then if they follow that rules, then they can be classified into one group. So let's say what are the certain rules? Rules like we can say that closure properties. So rules like closure properties. And what do you mean by closure property? Closure property means product of any two symmetry operations. So I write two elements. Elements means symmetry operations. The product of any two symmetry operations. So product of any two elements. Elements means symmetry operations. Are in the group and the product, I mean the result, the square of each element must be the element in the group. Let's say if I talk about A, B is equal to C, or I can say A into B equal to C, that cannot be equal to D but E and F, and let's say in the group all will be the elements A, B, C, D, E, F. That's what the closure property says. So like this we discussed about of the closure properties since from class 10th, that if AB equal to C and in C, that we have discussed AB A into B that closure property means A into B equal to, let's say there is any property C, and this C may not be equal to D, and D equal to E and F, and all groups will lie in the symmetry elements. This we will discuss whenever we are discussing about that matrix. And second properties that should follow, that is each elements or one elements in the groups, one element in the group, one element in the group should commute all the should commute all other elements in the group. So we may understand that what we mean by this. The element means operations. So one operations in the group should commute with all other with all other elements in the groups. It means that after applying that elements, other elements remain unchanged. It means if the elements, sorry, or I can say that the elements do nothing operations to other elements, so the operations remain, so the operations so the other elements remain unchanged, so you may understand that on which what I am talking about. Which remains unchanged, will not do any changes. The elements do nothing operations to other elements, so the other elements remain unchanged, and these elements is named as, we know, that is E. So that is identity elements. So if I say in one words, what I mean that all groups should have or one in group one operations or one elements should be E. That what I mean. Okay, so that means that whenever you apply like any C3, if you apply E, then it again come to be C3, means this remain unchanged. Similarly C4, if I apply E, then it is C4. Means with any elements, with any operations, if we apply E, then the operations remain unchanged and the same operations will come. So this is the second rules that a group should have to be fall in a group. And third rules, that the multiplications of elements should hold the associative law. This is the third property. They should have the associative law. Like say, if I say that any groups, let's say any symmetry operations or element, any symmetry operations A into B C is equal to A B into C. This should be followed. And fourth rules, that is every elements should have inverse, and the inverse should be the element in the group, should be the element in the group. It means that if I say simply, then every element should have an inverse element. Let's say if I say that C3, then it should have that C3 inverse, and then this inverse, whatever the result, that should be the element in the group. So these are the four certain rules that a group should follow. To be a group, this property that has to be followed, that closure property should be there in that groups, and one element that E should be there, which combines with all others elements in the groups. Element means symmetry operations. Another is that in the group, that associative multiplication element in that group, associative laws should be followed, should be held, and every elements in the groups, they should have inverse, and inverse also, that should be element in the groups. So if these four rules is followed to any groups, then that groups is characterized as one group. So likewise, the groups can be classified into various types. So you understand that what do you mean by group? Group means these four rules that has to follow. If anything follows these four groups, then we consider that as a one groups. So likewise, we have the different groups, point groups. So that's why this is called point groups. Why point groups? Means why are saying the point groups, that at least one point in the molecule in space remain unchanged. So if that will make a group, then on that group at least one point in the molecule in space, means in the molecule that is in space, remain unchanged after all operations. So after all operations also, that point will be remain unchanged. So that's why we call that point is known as when the point groups, means that point will remains unchanged, remain as it is, even if all the operations are done, whatever the operations in the groups. Elements means operations, so all the elements if you do, then also that points remain unchanged. So you understand that what do you mean by point groups? Okay. Now let's discuss that different types of point groups. Means that point groups we have for classifications of point groups. Classifications of point group. Classifications of point groups. Classifications of point group. So groups can be classified into, let's say that one groups has no rotational axis, means group with a group having no rotational axis, so that groups we consider as least symmetry group. And other second, this is the first types, and second types we can say that is group having single rotational axis. So here no rotational axis, here now single rotational axis is present. Single rotational axis. And third types we can search some groups having more than one rotational axis. And fourth types we will discuss. So this more than one rotational axis means this axis, these are dihedral groups. And the last types is octahedral groups. They are more number having more number of rotational axis, and this is highly symmetric groups. These are highly symmetric groups. So I will discuss one by one. Let us discuss about a group having no rotational axis. The first category we will discuss, that is group having now rotational axis. So that is called least symmetry group. So if I say that examples, so these all group means they should follow that 4 rules. Like it should follow commutative properties, and it should have one element which commute with all the other elements, and it should follow associative multiplication rules, and it have one element which is all elements should have inverse, and inverse is in the element of the group. So these 4 rules if follow, then only we say that is a group. So all the group means that is following that 4 rules. Okay, so one first group, point group. So point group means that follow that 4 rules. So first, least symmetry means group having no rotational axis. So first we can discuss about least symmetry groups. First we will discuss about of C1. So if I discuss about of C1, these elements H no rotational axis. Group having no rotational axis means rotational axis is not present. It is only having E. Okay, so it is only having E. So what is the example we can say? We can say that any molecules which is not planar, let's say here Cl, let's say here Br, let's say or I can write, it's safe to write, like if I write like this, then I can write any A, B, C and D, and this is not a planar molecules, and all the elements are different. So this have only E as the elements. Also have discussed that group should have 4 rules. So that first, that if every element should have E, like that if it commute with all other elements. So if no elements is there, E must be there. So first group is C1 only E. Okay, the examples we can talk like this. And second type is we can discuss about of CS. What are the symmetry elements present here? That is E plus sigma. So here sigma is present. So if I talk about of the examples, then we can talk like N S O. This type of groups means this is the planar molecules. So no symmetry is there except that it is having plane of symmetry, means molecular plane is there. Okay, so that groups is present with all the groups, and sigma, that is here this, since this is a planar molecules, so molecular plane is there. So that type of groups we consider as CS. And third type if it is cos, that is CI. So here you understand E is present plus I is present. I will write little bit distance. CI is present plus I is present. If I talk about of examples, then we can talk like here any F is there, F, H, H, CF and CL. Here only that identity I is there. Like if you go here, then you get one F, you get H, 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 CL, 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 CL. With that no other groups, because all groups are different. See, in the fronts, these are in the fronts, they are different. In the back, this is back, they are also different. But the I is present, because if you go from this point, so you will go this point, you will get the objects. Okay, so these groups are with group having no rotational axis. Now we discuss second types, that is group having single rotational axis. So now that is group having single rotational axis. Single rotational axis. So what are the groups? So let's talk. First groups we take around CN, means one rotational axis CN. So in these groups, what are the symmetry elements? E is present to all the elements. So you know that it is a group, means it has to follow that power rules. In power rules we say that E should be present, which is commute with all other elements, all other operations E. Okay, so this is the first groups. So E must be present in every groups. And what are all other groups should present? This should be CN is present, and if CN is present, CN means CN1, CN2, CN and -1. This amount of this CN means this is present. Okay, and only this. If I talk about examples, then let's say C2. So here what is the present? E plus C2 1 and C2 2 is again E. So only C2 1 is present. Okay. So if I talk about of the examples, I can talk about of that often book. So this H, this is H. So here if we rotate about of that C2 axis, then this will be come here, this will come here. Okay, so C2 axis is present. This is in the often book. Similarly, we can talk about a more of CN axis. So now we'll discuss on second type. So you can say about of any CNB molecules. CNB molecules means that what the axis are there, one rotational axis. So CN is present, and we know that whenever CN is present, either NC2 is present or no C2 is present. Similarly, if CN is present, either N sigma B is present or no sigma B is present. Okay, so now CN is present. So if we get any C2, then we say that N number of C2, otherwise no C2. If we get any sigma, then n number of sigma b, or if we not get anything, then no sigma b. So Cn. So in these molecules, b is there, means I have written n and b, means we understand that b is here. Okay, whenever CNH means H is there, here CNB means b is there. So it must be b is there, sigma b, and we know that if one sigma b, then n number of sigma b is present, and E is present with everyone. Okay, so these are the elements. Let's talk about our examples. We can say C2B, sorry, we can talk about of the C2B. So here, like water. So here what things are present? Here C2 is present. Okay, so C2 is present, then n number of C2 should present. Okay, so but here the principal axis itself the C2, and so here C2 is, here C2 itself is present, so C2 is present, but n number of C2 here, because this C2 itself is the Cn and n number of C2, so same, so only one C2 is present in this case. Okay, and next, sorry, first E is present, first E, then C2, and if Cn is present, then n number of sigma b is present, means 2 sigma b is present. Okay, for water molecules. So now we discuss about of that next. If we discuss about of that, these were second types. Okay, third, if I discuss about of CNH. CNH means E should be present. After that, any Cn axis is present, and Cn axis means you know that either n number of C2 or no C2. Always remember that Cn means either n sigma b or no sigma b. Okay, so here Cn is present. So now we'll say that whether sigma b is present or not. Here H is present means definitely sigma H is present, and we know that sigma H is 1 sigma H or no sigma H. For sigma H case, either it present 1 sigma H or no sigma H. So 1 sigma H, so no more sigma H is present. Means if sigma H is present, then only 1 sigma H is present. Otherwise, no sigma H. Okay. So Cn is present, then sigma H is present or not. So here since sigma H is already present, so here sigma B is not present. Let's say sigma B is not present because sigma H is present. Okay, so let's take examples. If we say that any molecules like maybe the picture may be wrong, but this type of molecules. Okay, so here that what these molecules have C3, so C3H, here E is present plus C3 is present, and that this is the planar molecules, so sigma H is present and sigma B is not present here. Okay, so this type of molecules. And we know that if C3 and sigma H is present, so for S3 what should be present? S3 or any Sn, what should be there? Sn, any sigma or any Cn perpendicular sigma H is present, or sigma H Cn is present for Sn. So here see, this is the C3, this is Cn, and this is sigma H. Then definitely here C3H is present, C3 is present, then definitely sigma H is present, then definitely S3 is present. Because if that sorry, if C3 and sigma H is present, then definitely S3 will be present. Because for Sn or any S3, S4, whatever, that for containing this that the Cn should be present and sigma h is present. If this is present, then this is must be present. Okay, if this is not present, then for even case it may or may not present, and for odd case, if it is not present, then it is not present. But for even case, if it is present, if it is not present, this may or may not present, that we already discussed. But if this both are present, then this must be present. Okay, so here that S3 is present because A3 and sigma h is present. Now we will discuss on C3B's CNH we have discussed. Now we will discuss about other facial groups, that is C infinity B. C infinity B. This is all types. All types C infinity B. This group is called as special type of point groups. Type of point groups where the linear molecules without center of symmetry are fall in this category. Let's say that any like HCl, HBr, HI, whatever, that not linear, means linear molecules, but their center of symmetry is not there. So see here H, C, so from here you get H, you get Cl, so different. So I is absent, and in these groups, if this is the principal axis that we already discussed, the C infinity, and here also the C2 is absent, C2 is not there, C infinity is there, and here through this we can pass sigma b also. It means one sigma b is there, then C infinity sigma b is there because C and then n number of sigma b. So what are the group elements for C infinity B? One is E is there, that is always it should be there. Another principal group is C infinity, and here one sigma b is there, then infinity sigma b is present. So these are the groups for these elements. Okay, now we will discuss next type of groups, that is dihedral point groups. So now we will discuss third types, groups having more than one rotational axis or dihedral groups. Now that fourth category is 4 or third, that is 1, and this is third types. Okay. Groups having single rotational axis. Okay, this is the third types. So that is group having more than one rotational axis, that is dihedral groups. And note that whenever you say that dihedral, means that that principal axis Cn perpendicular to n number of C2 axis. Dihedral means that Cn perpendicular to n number of C2. This is what we mean by dihedral. And we also know that dihedral plane means any C2 is, what you say, that like we have discussed, it is Cl and Cl. So if I say this is C2 axis and this is C2 axis, then the planes the planes which cuts this, means in between this axis, this and this axis, this plane is cutting, so this plane is called dihedral plane. Or this way, this same can be explained as like other case I can say PT, CL and CL, CL and CL. The same case if I explain that that any planes if we pass, let's say I'm passing this one planes here and this other planes if I pass here, then the in between that one axis is there one angle. So if the C2 is passing to this, then this C2 is passing this, bisecting the angles formed by two dihedral planes, formed by these two planes. So now these planes are called dihedral planes, Okay. So now why I'm discussing about of this dihedral and dihedral plane, because the dihedral means more than one rotational axis, that is Cn perpendicular to NC2, that is principal axis, Cn is principal axis perpendicular to C2 axis. So here we are talking about C2, here also we are talking about of C2. So C2 must be present in dihedral groups, and that C2 should be perpendicular with principal axis. Okay. So first groups in this will take about of Dn. So what are the symmetry elements should be present? First is A should be present, and since here this is the more than one rotational axis, and we know that D represent dihedral. So if dihedral means any principal axis Cn is there, then with that what is there? Cn perpendicular to NC2 is there. So this is one symmetry element, this is two symmetry, this is another symmetry element, that means N perpendicular to C2, that NC2 is there. Or this is also you can write simply as NC2, this is present. After that what is present? Is Cn and NC2. So let's start that example if it says okay, 1 2 3. So these groups, these symmetry elements will be present. And if I talk about a second page, let's say D and V, D and V point groups. What are the elements to be present here? E, Cn plus Cn perpendicular to NC2, this is present, and means this is NC2, it means this, or also you can write NC2 is present plus sigma B is present, and you know that if one sigma B is present, let's Cn, one sigma B, then n number of sigma B, so n sigma B is there, and C2 is already present, n number of C2 perpendicular to Cn. So this we can take the examples like any groups, that groups you can say that cobalt, we can say that here NH2, here NH2, here NH2, here NH2, here NH2, here NH2, and what this and this are planes like this. Now that C here that C3 axis is present, C3 axis. So one C2 axis is passing, C2 axis will be passed like this, and another it will be, and another's will be C2 axis. Okay, so here that C3 is there. This is example of D3B. Or this is sigma H is that, no, this is the D and B examples, E, C, and N, C2s and C2 and N sigma B. Okay, first let's talk all the examples. And third groups we are having, that is D and H point groups, or you can say that D and D point groups. D and D group one first. So let's look about D and B point groups. Sorry, this is not D and B point groups. This is, we'll discuss these point groups later. This is the examples of D and point groups. Okay. So now let's discuss about of the D and D point groups. So if I talk about D and D point groups, then what are the D and D point groups? What are the symmetry elements it presents? That should be, one is E, one should be E, and another is Cn, another is Cn perpendicular to NC2. Note that this means only NC2 is present. Okay, this or this, anyone I can represent. And another is D is there. So any dihedral plane should present. So any dihedral plane group, and if one, then must be that ND. Okay, we will take the examples that will be makes us understand clear. Let's say any D3D point groups. For these point groups, what things are there? It's the examples of, we have discussed that staggered ethane. Staggered ethane. Staggered ethanes, like say we can say that these groups. So if I write in Newman projections that we have discussed already, so this, so here what we say that, here that sigma H is absent. We already discussed these examples, and here also that C6 is absent but S6 is present. So if I note about of that D3D point groups, here D3D point groups, what things are present? E is always present. After that, here C3 axis is present, C3 is present, but no, C6 is not present. And after that, N, that is 3 C2 should present, sorry, 3 C2 is present, that is Cn, that is C3. I will write in somewhere else, I will write below. Okay, D3D means E is present, C3 is present, and C3 perpendicular to 3 C2, sorry, 3 C2 is present, or this we can write 3 C2 is present. After that, what things is present? After that, S6 is present. And now since here that sigma is present, like, you know, if I cut these molecules, then that will be reflect. So sigma B is present. Now in this case, this is the dihedral, this is cutting this angles. This is the dihedral plane. So if dihedral plane is means dihedral angle is there, that means one sigma b and one sigma b is there. And we know that if that dihedral plane is there, dihedral angle is there, and if that is sigma d, if sigma d is there and sigma h is absent, then what you know that if sigma h absent and sigma d and sigma b is present, then what we know that all sigma b are considered as sigma d. Okay, this we already discussed in the first class, that if sigma h is absent and sigma d and sigma b is present, then all sigma b are considered as sigma d. So here this all sigma b and d is considered as only sigma d. So 3 sigma d is present, because C3 means either n number of sigma b is present or no sigma b is present. So here C3 is there, so 3 number of sigma b is there. But since here sigma h is absent and dihedral plane is there, so all sigma b are considered as sigma d. Okay, and now the d and d point groups we have discussed, and d and point groups we have discussed. Now the last point groups for this dihedral, that is d3h. d3h point groups. So what are the elements with there? One, let's say this is 2, let's say this is 3. So what are the symmetry elements to be present? So if we looking like this, then E is present, so D means C3 and another is C3 perpendicular to why not D and H, that I can generalize, right? So we write D and H. So what are the symmetry elements? E plus Cn and another will be Cn perpendicular to and C2, or you can simply write NC2, and another thing is that here H has come, so here sigma H is present. And note that if that Cn and sigma H is present, always remember, if Cn and sigma H both present, then S and H must be present. Either n is odd or even, all the case. If Cn and sigma H is present, then this condition should be always remember. If this is present, then sigma H is definitely present. So here what? Sn is present. Okay. So if you take examples, like we take about of BF3 type of molecules, like here F. So this is perpendicular principal axis is C3. So this is D3H. So this point groups like 3, sometimes I say 4, sometimes like 5. So this 4 and 5, it's coming from this principal axis. Since here principal axis is C3, that's why we write D3. If principal axis is C4, then we can write D4. Okay, so here principal axis is C3, so this is D3H point groups, because C3 is present and that sigma H is present. What are the symmetry elements for that? E plus C3 plus C3 perpendicular to 3 C2, or we can simply write 3 C2, and we have sigma H is present and we have S3 is present. Okay, so in this groups we can see that here sigma H is present, and we have also C3 axis is here, this point groups. Okay, C3 axis, and sigma H is present, and since H3 is also present in these point groups. So these are the symmetry elements for this point group. So these things will be present for this point groups. Okay. Now we'll discuss that another type of point group, that is special type point groups. You can say that is D infinity H. So this is a special type of point groups. Special type of point group. Point group where the linear molecules with center of symmetry. So let's say that any molecules like CO2, H2, this is CO2, H2, Cl2, all this type of molecules means where the linear like if I talk about C, so here what is there, if you go here and go here, same molecules, here space, so this is I is present. So in this D infinity point groups, so first D means C infinity, here the principal axis is C infinity, and if C infinities and first is E plus C infinity, and here D means that C infinity perpendicular to infinity C2, because here C2 axis is also present. Here this is C2 axis, so n number of C2 axis is there, like here, and if you write here, so all are C2 axis, means n number of C2 axis is present. So this axis we can say that this is a linear molecule, so we can pass C2 anywhere because both are same. So you can pass either this side, or if you little angle if you change, then also C2, like that n number of C2 axis is there. Yes. So here if we say that both are, if they both are the oxygen atoms, means here also oxygen, here also oxygen, it means that if we pass C2, then they will get the equivalent structure. So either you pass C2 like this in the straight manner, or if you like this little tight tilted, then also if you pass C2, then also you will get equivalent structure. So n number of C2 axis you will get. Plus what things is there? So you see that this is the principal axis. So this is the principal axis, this is C infinity is the principal axis, and here that if I pass any planes, here, then that this bisect this and this bisect this, and this C infinity, these are perpendicular. Okay, so means sigma H is present, and if we pass any angles that from here to here, then also it cutting oxygen, carbon and oxygen, so this plane is there, sigma B is there, and if one sigma B, so n number of sigma B is there because Cn, then n number of sigma B. Also you can see that here we are cutting another, we can cut like this, so which is cutting all the elements, so n number of sigma B is there, and important thing is here I is also there. Okay, so E C infinity, then NC2, this is there, sigma is there, and n sigma B is there, I is there, and you know that if C infinity, that is Cl, and also we have that H, it means S infinity is there. Okay, so what I have discussed for S, this is that n equal to even for Sn, n equal to even, then what we say that if sigma H and Cn both exist independently, means both are present independently, then Sn must be present. This is n equal to even or n equal to odd. This is the first conditions we have seen, and second conditions what we have seen, that if n equal to even, then if sigma h and Cn both not exist independently, so Cn is exist always, right? So if because Cn is always exist, like whatever the C3x is, C2b, D3, D3x, always C3 is present. So if C3 or if Cn is always exist, it is always exist. So now condition is sigma h. So if Cn exists and sigma h absent, means that sometimes that C3 is exist, but that let's say in this case see, C6 is absent but S6 is present. Here the principal x is C3. So for that case, looking on that, so we say that if Cn and sigma h both absent, if n equal to even, both absent, then also Sn may or may not present. Okay, and if Sn is present, and here 2a, so if sigma h absent, if sigma h and Cn absent, then S2n can be present. This have to look. So if both are absent, then, or if the sigma h is absent, then look that S2n can be present or may not be present. Like these examples we have seen that which case, this case, see, C6 is absent, sigma h is absent, but S6 is present, principal x is C3. So here C3 and sigma h absent, but that S, this is 3, so 3 into 2, that is S6 is present. That's why I said that if Cn and sigma h and Cn absent, then S2n can be present if n equal to even. Okay, this is the second point you have to remember for that. And third point is that for this points only, why this S2n? Because this is the regions of what, that if sigma h and Cn absent, this is the regions why these conditions we have applied, because S2n presents, then Cn must be present. If S2n present, then Cn must be present. This is the ultimate, means this is the must. If S2n is present, then Cn must be present. This also we studied in different way, that Sn presents, then Cn by 2 axis must be present. That we have discussed. So since that I can there, this is the if S2n is present, then Cn must be present. If I do the inverse, then inverse is may or may not. That we already discussed, that if Cn is present, then S2n may present or may not be present. That's what we discussed, that if sigma h and Cn absent, this Cn, if sigma h and Cn is absent or Cn is present, that is Cn sigma h and Cn by 2, Cn is absent, then S2n can be present. That's what we discussed here, that if S2n is present, then Cn must be present, or if Sn is present, then Cn by 2 axis must be present. But vice versa may not be true. If Cn2 axis is present, then Sn may or may not be present. That's what it means. Vice versa may not be true. So these are the conditions, like for n equal to even, these conditions you have to look it. So if n sigma h and Cn is absent in any case, then you have to look that S2n can be present, because there we have discussed that S2n is present, then Cn must be present, or Sn is present, then Cn by 2 axis, n upon 2 axis must be present. This is for the even, and for that odd, what you say, that if sigma h and Cn absent, n equal to odd, this case, then Sn also absent. For the n equal to odd, there is no such condition. If this is absent, then Sn is simply absent. Okay, but n equal to even, if that is absent, then also S2n can be present. Okay, so that we have discussed in the previous class. So from here we say that sigma h and principal axis is present, then S infinity must be present. So this is all about of that dihedral groups, that is axis having more than one rotational axis. So this is about of this point groups. So today up to this, in next class we will discuss more. Thank you.